Shalom and welcome once again to Checkpoint Training Bytes. Checkpoint Training Bytes is where we bring you advanced training on different products, features, and blades. My name is Manuel Joel King. I will be your instructor. In this module, we'll be looking at CoreXL, and this is part 2 of CoreXL technologies. Okay, so let's get started. Let's take a look at the agenda of this module. The first thing we're going to do is discuss the open performance architecture. We'll discuss what these architectures are, and then we'll discuss CoreXL, SecureXL, and ClusterXL, and how to optimize and improve performance and security by using these open performance architectures. And then we'll discuss the processing path, how a packet flows as it's being processed by the different architectures. And also we'll look at some best practices when combining these different architectures or breaking up these different architectures. And also we'll discuss the user space processes, how these user space processes communicate to the different architectures. And then we'll look at some limitations like VoIP limitations, and also we'll look at VPN limitations, and we'll discuss how to optimize and enhance and work around these limitations. Let's talk about CoreXL. CoreXL is part of the Open Performance Architecture. Open Performance Architecture is a framework of technologies designed to accelerate and optimize security performance. And these technologies uses the SecureXL, ClusterXL, and also CoreXL technologies. And so you can use these three technologies independently or combine the three technologies and make them work together to gain advantage of each technologies for optimal security and performance. So let's discuss the three components. These three components are, as we know, SecureXL. SecureXL could be either a software acceleration done at the driver level or a hardware acceleration done on the ADP cards or the SAM cards. And SecureXL, we can have packet rate acceleration, which is also called throughput acceleration. And we can also have acceleration for connection rate acceleration, also commonly called template acceleration. But as you know, certain traffic cannot be accelerated. And so we bring CoreXL into the picture. CoreXL, as mentioned before, it uses parallel security gateway kernels running in instances, and each instance is running on its own dedicated core. And so we're leveraging the modern processor architectures. And we can take advantage of what we call medium path, which I'll explain coming up in a few slides. And so we can combine both SecureXL and CoreXL technologies in addition with ClusterXL technologies that allows us to do load sharing in an active-active clusters or a high availability solution for security gateway resilience. And so let's review what we discussed on the previous video. In the previous video of CoreXL, we talked about firewall instance. The firewall instance can only run on the specific CPU. You cannot have multiple firewall instances, and that was because only one CPU could actually process data at one time. And this was due to a monolithic lock that was needed to preserve and protect data structures. And so a multi-core system platform actually behaved like a single core system. So in some instances, if the customer does not have multi-core systems, he can still get acceleration by using Performance Pack or SecureXL. SecureXL comes in two models. We have the software model and we also have a hardware model. In the software model are actually drivers that you install at the kernel level, and at the hardware level we have two cards. We have the original ADP cards. The original ADP cards came from the Nokia purchase, and you can install ADP cards on the IP appliances. And we now have the newer cards, which are called the SAM cards, Secure Acceleration Modules. And the Secure Acceleration Modules, you can install these on the newer 2012 appliances. So depending on the traffic profile of the customer, depending on the certain traffic, the traffic could be accelerated at Performance Pack level. Or, as you know, some traffic cannot be accelerated at the SecureXL level, and so those traffic needs to go to the firewall for processing. Now, in some environments, depending on the customer's traffic profile, a lot of traffic might need to go to the firewall for processing. And so in those cases, the customer would be best served if he purchased an appliance that could support multi-core systems. And then in addition, he will purchase CoreXL, and so he'll have multiple firewall instances. And in addition, with multiple cores, he can combine CoreXL with SecureXL, so the traffic could be accelerated at the SecureXL level. And certain traffic will be accelerated at SecureXL level, and other traffic will need to go to the firewall for processing. So now let's recap what we've discussed so far. In this example here, I have 4 cores. The dispatcher is going to be running on one specific core, and we have 3 firewall workers, and these are what we call firewall instances, and these instances will be running on their each independent cores. And each firewall is actually an independent firewall running the same policy. And so the dispatcher is installed on one core. The traffic that coming into the NICs will be assigned to the same core for processing as the core that's running the dispatcher. Now, if we enable SecureXL and add SecureXL on top of CoreXL, SecureXL will run on the same core that's running the dispatcher. So the dispatcher and SecureXL Performance Pack will run on the exact same core. And so this core is what we call the SND, Secure Network Dispatcher. The Secure Network Dispatcher is the dispatcher plus it's doing security for SecureXL. So the Secure Network Dispatcher maintains a few tables. At the dispatch level, it maintains the global dispatch table. At the SecureXL level, it maintains the SecureXL connection tables and the SecureXL templates tables, plus other tables like the drop tables, the templates tables. And so the Secure Network Dispatcher must forward all packets of a connection to the instance which handled the first packet. And this is important not only for functionality, but also for performance. So the Secure Network Dispatcher is responsible for 3 things. The first thing that it's responsible for is processing traffic that comes from the network interface card. So all traffic coming to the interface cards need to be processed by the Secure Network Dispatcher. The second thing that it needs to do is secure accelerated packets. And so if a packet needs to be accelerated at the performance pack level, it will be accelerated by Secure Network Dispatcher. And the third thing that Secure Network Dispatcher does is distributes non-accelerated packets amongst the kernel instances. So it must distribute all non-accelerated packets amongst the firewall instances. So let's take a look at another example here to help clarify Secure Network Dispatcher. Let's assume that the Secure Network Dispatcher is assigned to core 0, and there's a lot of traffic coming in to ETH0 and a lot of traffic leaving ETH1. And so we have high CPU on core 0. So one thing we could do is change the affinity of core 1. Instead of having core 1 assigned to firewall worker 2, we can change it to also run a dispatcher. So now that the Secure Network Dispatcher is actually running on 2 cores. And so because we have 2 cores, we no longer have high CPU issues for inbound packets. And any traffic that needs to leave on, let's say that traffic needs to leave on ETH1, any traffic that needs to leave on ETH1 could be processed by either core, core 0, or core 1. This is what we call automatic affinity. Automatic affinity means that traffic can be processed by either core automatically. And so every 60 seconds it runs an algorithm, checks the load on the cores, and redistributes the load depending on how busy they are. Another point I want to make, since I did not make it already, is that the firewall instance and the Secure Network Dispatch instance actually should be running on 2 separate cores. They should not run on the same core. And this is important to note because when you set up CPU Infinity or SIM Affinity, you don't want to mix them. For example, the CPU Infinity, when you're setting up firewall instance, you want to be sure that the firewall instance is actually running on a core that's not running Secure Network Dispatcher. Or if you're setting up process affinity, you want to be sure that the process affinity is running on its own core and not a core that's shared with the dispatcher. But the reverse is true when you're setting up SIM affinity. When you're setting up SIM affinity for interfaces, you want to be sure that the interface affinity is assigned to a core that's running the dispatcher and not to a core that's running the firewall instance or process instance. There is one exception to this rule, and the exception is if you're using 2 cores appliance. If you have an appliance with only 2 cores, then it's not ideal to have the dispatcher running on 1 core and the firewall worker running on the another core. I mean, you could do it, but it would not be efficient because you might run into issues where traffic needs to be accelerated, and so the CoreXL might be the bottleneck, or traffic might not need to be accelerated, and so traffic will need to go to the firewall for processing. A better or more ideal solution is to actually share the cores. So core 0 is shared with firewall worker 0 and also the Secure Network Dispatcher. And core 1 is also being shared with firewall worker instance 1 and also the Secure Network Dispatcher. Let's take another example here of a packet as it comes into ETH0. ETH0 needs to interrupt the CPU. assume that we have automatic affinity enabled. It's going to interrupt the least utilized core. Assume that core 1 is the least utilized core, so ETH0 is going to be processed by core 1. The packet arrives at the dispatcher. The dispatcher also uses core 1 for processing. It looks in the dispatch table. That connection is not known, so it forwards it off to the firewall for processing. The firewall needs to process that connection. Again, it uses the same core 1. Assume that the packet was accepted, forward it back down to the dispatcher, updates the dispatch table about that connection. Then that packet is going to leave, let's say, on ETH1. ETH1, again, it interrupts core 1, processes that connection, and forwards it on its way. So let's talk about best practices when we talk about kernel instances. Kernel instances are also known as firewall instances. So if you have a system with one core, CoreXL is disabled. That means you have one core and one core is running the firewall, but you can't enable CoreXL. If you have two cores, then two cores are actually enabled for CoreXL, and so both of these cores are actually using firewall instances on both cores and also dispatching on both cores. If you have 4-core system, then ideally you would use 3 cores for kernel instances and 1 core is left over for the secure network dispatcher. If you have 8 cores, you want to use 6 cores for the firewall kernel instances and 2 cores are left over for the secure network dispatcher. And if you have a system that has more than 8 cores, the number of cores that you want to use for kernel instances is the number of cores in total that you have minus 4. These are equal to the firewall instances, and minus 4 is for the secure network dispatching. Now let's talk about ClusterXL combined with CoreXL. If you're using cluster in conjunction with CoreXL, you need to have the same amount of cores on both cluster members. So if one member has 4 cores, the other member should also have 4 cores. Now it is possible that physically one member has more cores, like let's say this member has 8 cores and another member has 4 cores. That would also work as long as the CoreXL license only allows 4 cores on this system and the CoreXL license allows 4 cores on this system. And so physically they might have different cores, but license-wise they have the same amount of cores, 4 on each side. Now I've seen the reverse of this, a situation where the customer had the same amount of cores, but license-wise he only had a license here for 2 cores and a license on the other system for 4 cores. Even though physically they have the same amount of cores, license-wise they don't match, and so you can run into issues. And the reason is that each instance, firewall instance 0, has to sync with firewall instance 0 on the member cluster, and firewall instance 1 has to sync with the member firewall instance 1. Firewall 2 instance syncs with firewall 2 instance on the other members, and firewall 3 will sync with firewall 3 on the other members cluster. Now just to clarify something, there's only one sync interface. Both sync interfaces are connected to each members, either a crossover cable or through a switch, but the firewall instances are actually being synced through the sync network. One is being synced through the sync network, and firewall 3 is being synced over the same sync network. So let's analyze a ClusterXL with CoreXL a little bit further under the hood. Let's say we have a packet that came in and a packet came into member A. Member's A dispatcher is going to look in his local dispatch table to see if that connection is known. He does not know about this connection, so he needs to make a decision. He makes an arbitrary decision. To be frank with you, it uses more than an arbitrary decision. It actually uses the 4-tuple information. The 4-tuple information that it uses is the source IP address, the destination IP address. It doesn't use the source port, but it uses the destination port, and also uses the IP protocol number, like 6 for TCP, 17 for UDP, and 1 for ICMP. Keeps track of this information, makes a decision where to assign this packet, and it's going to assign this packet, let's say, to firewall 2 instance running on member A. Firewall 2 instance is going to process that connection, look in the rule base to see if there's a rule allowing it, and if the rule allows it, once it updates its local connection table, it's also going to update the global connection table and process that connection and forward it on its way. And take a look at this. It actually is going to sync with member B. Firewall instance 2 on member A is going to sync with firewall instance 2 on member B. So firewall 2 syncs with firewall 2 on member B. Look what happens on member B. Member B is going to update its connection table. It doesn't need to process that connection. It just updates it in its kernel connection table. And at the same time, it also will update its global connection table. So now both members know about this connection because they both have it in their global connection table and also have it in their local connection table. So now take a look at this. The packet comes in. This time it comes into member B. Member B is going to be the member processing that connection. The dispatcher receives that packet. It looks in the dispatch table to see if that connection is known. And this time it is known because it was originally processed by Firewall Worker 2. So the dispatcher is going to assign it to Firewall Worker 2. Firewall Worker 2 is going to look in its local connection table to see if that connection is there. And it is there. So it's going to need to process that connection and forward it on its way. So now let's do this again, and this time we're going to use ClusterXL, CoreXL, and SecureXL. This time we've added a performance pack at the SecureXL level, and let's assume a packet comes in, and the packet comes into member A. So this is the first time this connection comes in, and so it's not going to be accelerated at the performance pack, so it's going to go to the dispatcher. The dispatcher is going to make a decision, is going to look in the dispatch table, connection is not there, so again it forwards it to one of the firewall instances, firewall instance 0. It's going to process that connection and then update it in its connection table. At the same time, it's going to update the dispatcher about that connection. Plus, if this connection was accelerated, it will update it in the SecureXL table. Now, potentially, this connection can also be templated, so we'll create a template for it. So when member A, firewall instance 0, updates it in its local connection table, it's going to sync that with member B's firewall instance 0, and it updates it in its local connection table. The local connection table updates the global dispatch table, and the local connection table also creates a SecureXL entry and a templates entry. So all subsequent packets will be accelerated through the SecureXL table on member B, or if they go to member A, they'll be accelerated at SecureXL table. Now let's assume that a packet comes in, and this time the packet comes into member B. This is a different packet, but this packet actually matches the templates table. So the templates table is going to create an entry, and it updates it in a SecureXL table. Now the SecureXL tables do not sync with each other. So how are the SecureXL table on member A going to know about that connection that was templated on member B? Well, if you recall, on Smart Dashboard, there's an option to start synchronizing connection after a certain amount of seconds. The default is 30 seconds. So only after 30 seconds will the SecureXL table update the firewall local table, and the firewall local table will update the global dispatch table. And member B's firewall instance 0 will then sync that connection with firewall instance 0 on member A's local dispatch table, and the local dispatch table will update the global dispatch table and will also update the SecureXL table. And so all subsequent packets could be accelerated at members A SecureXL table or accelerated through members B SecureXL table. Now, one other point I want to make is before member B synchronizes the connections with member A in the SecureXL table, those entries won't be here. Obviously, what happens if the packet arrives here before member B has a chance to synchronize with members A? Now, this connection won't be in a SecureXL table, and so if he goes to the dispatch table, again, it's not in the dispatch table. The dispatcher is going to need to assign it to a firewall instance. The firewall instance is going to inspect the packet, and it's going to see that the packet is out of state and drop that packet. And so when you're setting up clustering, you might want to use high availability to be sure that the connection is always assigned to the same machine. Or if you use a load sharing, load balancing solution, you want to be sure that the connection is either sticky or that you decrease the synchronization clustering timeout. So the next thing I want to talk about is what we call firewall path. Firewall path means, let's say that the packet came in, on ETH0. It's going to go to the SecureXL to see if that packet is known. It is not known, so it goes to the dispatcher to see if that packet is known. Again, it's not known. It goes all the way to the firewall. The firewall is going to process that connection, and this is what we call firewall path. The packet had to go all the way from the interface card all the way up to the firewall for processing. So this is called the firewall path. We can also call it slow path. It's slow path because it has to go to the firewall for processing. And so after the firewall processes that connection, it's going to update it in the dispatch table, and it's also going to update it in the SecureXL table and forward that traffic through. Now, because now it's in the SecureXL table, any connections coming back, let's say this was originally a SYN packet. Now this is going to be the SYN ACK packet that's coming back for the reply, and it's going to find a match in a SecureXL table. And so when it finds a match in a SecureXL table, this is what we call acceleration path. So now we have the packet is being accelerated and not going to the firewall for firewall path. And so when it's accelerated, we also call this fast path, because it's fast because it's being accelerated at the SecureXL level. Let's assume that the packet is fast pathed. So the packet comes in and it's going to be accelerated at the SecureXL level, but we need to do deeper inspection. We can't just accelerate it, because acceleration is just going to look at the source IP address, destination, and the 5-tuple and forward that traffic through to SecureXL. But we need to go deeper down at the packet level and inspect that packet. Maybe this is a HTTP connection and we've enabled in IPS some HTTP signatures, and so we need to go deeper down at the packet level for inspection. And so Checkpoint has come up with a solution called medium path. So medium path refers that the packet is found in the SecureXL table. So the packet is found in the SecureXL table, but we can't just accelerate it because we need to do deeper inspection. And so what we do is we send the packet up towards the firewall, but it does not need to be inspected by the firewall because the firewall has already looked in the rule base and allowed that connection. That's why it was here in the SecureXL performance pack level. And so we just need to do deeper inspection. And so some of the blades, like the IPS blade or the app control blade, will be running on the same core that is running on the firewall. And so the packet comes in, it doesn't need to go to the firewall, it's just going to be inspected at the IPS level or inspected at the app control level. And so this is what we call medium path. And so a packet that's processed by medium path is being processed by the PSL, passive streaming layer. The passive streaming layer, it actually collects all the packets for deeper inspection. So the packet streaming layer, we also call that the PXL for packet acceleration. And so passive streaming layer or PXL layer is only available when you're running CoreXL. If CoreXL is disabled, then medium path does not exist. Only when you have CoreXL with multiple cores can you run it in medium path. And one other thing I want to leave you with, as I mentioned already, slow path is also called firewall path. So slow path and firewall path really means the same thing. And I mentioned also that fast path and acceleration path really meant the same thing. And so if you say the packet is being accelerated in acceleration path, you're actually meaning it's being fast pathed. Also, if you're talking about medium path, you can actually say PXL. But in addition, if you're running some diagnostics commands, you might find information relating to F2F. F2F refers to forward to the firewall. Forward to the firewall is referring to firewall path or slow path. You might also see F2P. F2P is referring to forward to the passive streaming layer. So forwarding to the passive streaming layer is the same thing as medium path or PXL. The next thing I want to talk about is some of the best practices with regarding to SecureXL, CoreXL, and ClusterXL. Should you always use these three products together? In some cases, you might have all three products running together. In some cases, you might only want to have one or two of these products, depending on your traffic patterns and traffic profile of your network. In some cases, SecureXL has limitations, CoreXL has some limitations, and ClusterXL have limitations with regards to different packets, different traffic profiles. For example, a lot of traffic cannot be accelerated at CoreXL, and so you might not need to have a lot of CoreXL instances. You might want to have more SecureXL instances, or vice versa. There might be a situation where you might need to change the affinity of, let's say, this core and have two cores assigned to the security network dispatching. And so there are certain commands, which I will show you later, that will help you identify high CPU utilization on your appliance. So as an example, maybe your secure network dispatcher has a lot of a high CPU. So what you could do is have more cores for the security network dispatcher. So in this case, I actually have 4 cores that are being used for dispatching. And that could be because I have a lot of traffic that needs to be accelerated. Traffic needs to be accelerated Maybe I have HTTP traffic, TCP traffic, UDP traffic, a lot of that kind of traffic on my network that could be accelerated and can also be templated. And so I want to accelerate this traffic over SecureXL. And so I might need less CPUs for my firewall instances. But the reverse might be true. Maybe I don't have a lot of traffic that needs to be accelerated. So some traffic will be accelerated through SecureXL, but most of my traffic needs to be either firewall inspected and it has to go to the firewall for firewall to inspect it, or it needs to go up to the passive streaming layer for maybe IPS inspection, application control inspection, or other deeper inspection. So for example, maybe I'm not using SecureXL, and so if I'm not using SecureXL, I don't need multiple cores to run SecureXL, and so most traffic is going to be dispatched at one core and being dispatched to my firewall instances and going to my firewall instances either for firewall inspection or IPS inspection. Or maybe I have a cluster and a lot of my traffic needs to be synced, and so I might need an additional core to run dispatching because these cores are also doing the syncing in the cluster. Now, so far, I've only been talking about the kernel. The kernel is where the firewall instances run, firewall instance 0, firewall instance 1, also where the dispatcher runs, plus the SecureXL also runs at the kernel level, either at the driver level or at the hardware level. And so far, I have not talked about the user space level. Above the kernel level is what we call the user space level. And at the user space level, this is where we have our firewall daemons, our FWD daemon, our FWM daemon, VPN daemon, etc. I have another diagram here to help us clarify this a little bit better. And so all these daemons, they have to communicate to the firewall instances, firewall instance 0 and firewall instance 1. Now at the user space level, we run a user space process called the FW worker 0. FW worker 0 is a process at the user space level that represents the firewall kernel instance at the kernel level. And FW1 worker is the firewall worker that represents the instance for firewall 1 instance. And this is good because it helps us identify what user space processes are using a lot of CPU. So if I look at the user space process, maybe I use the top command or the vmstat command to identify what are the most utilized processes. I can see that if the FW worker 0 is actually the instance 0 that's using a lot of CPU or not using a lot of CPU. The same thing if I see multiple workers, worker 1, I can identify how busy worker 1 is at the kernel level by looking at the user space level process called FW workers. And one other thing I need to stress is that the user space processes are not replicated. And so there's only one user space process, and if those user space processes needed to communicate to the kernel, which kernel instance will those processes communicate to? For example, I want to see what the firewall version is. FW space ver, I hit enter, which kernel instance is going to process that request? Well, the default is always going to be processed by kernel instance 0. Kernel instance 0 is going to process the request, and if need be, the firewall kernel instance 0 will also communicate to the other kernel instances, make the requests to those kernel instances. Those kernel instances will provide information back to kernel instance 0, and then kernel instance 0 will provide the information back to the user space level. Let's take a look at another example. Let's say you want to view the firewall tables. FW tab to view the firewall tables. You type that at the shell. The shell is going to request that information from the firewall worker 0 instance. Firewall worker 0 is going to make a request to all the other instances. And then it's going to aggregate all the information and provide information back to your shell. Let's take another example. Let's say that you want to push the policy. So you go and push the policy. The FWD process needs to enforce that policy and push that policy down to the firewall instances. And both instances or all instances need to enforce the same policy. If the policy fails to install on any instance, then all instances will revert back to the older policy. And so only if the policy is successful to be installed on all kernel instances will this new policy be enforced. And so another thing I want to point out is some limitations. Some limitations, for example, with VPN. VPN state is per tunnel and not just per connection. And so per tunnel you might have a bunch of connections. And so how is the dispatcher going to keep track of all these different connections that are established through one tunnel? And so the solution is to keep all VPN traffic running on Firewall Instance 0. Firewall Instance 0 will have all the VPN traffic, and all connections through the tunnel will have to go through this instance. Now that can lead to some performance issues. Obviously, if you have a lot of VPN traffic, all VPN traffic will be assigned to instance 0, and sometimes you have other instances that are underutilized. Also, another issue that sometimes you might encounter is if you have a lot of voice over IP traffic. Voice over IP traffic also has to be assigned to the same instance, kernel instance 0, because voice over IP traffic has different sessions, like the signal session and also the media session. And it's a very complex protocol because you also have, in addition to the different sessions, you also have different streams, like your audio stream and also your video stream. And these streams and sessions and connections need to be assigned to the exact same core, because if it was assigned to different cores, then you can run into issues where packets are getting dropped either out of state or latency issues. But there is some good news. There is a kernel parameter that you can change so that you can assign all the VPN traffic and VoIP traffic to kernel instance 0 and distribute all other traffic to the different other kernel instances. And in addition, starting with R77.20, we do have a VPN fix for SSL traffic, and so now you can distribute SSL traffic amongst the different firewall kernel instances. And in future releases, we're also coming out with a fix for IPsec VPNs, where we can distribute IPsec traffic amongst the kernel instances. So let's summarize what we discussed in this chapter. First of all, we looked at the open performance architecture. These open performance architectures are the SecureXL, CoreXL, and ClusterXL technologies, and these components can work together, combine together, or separately to improve performance and enhance security. Also, we talked about CoreXL and SecureXL and ClusterXL, how these components work when they are merged with each other. And also we talked about the processing path. The processing path is where a packet has to go through all the way to the firewall for processing, and this is what we call the firewall path. The firewall path is also known as slow path. Slow path means that the packet has to go all the way down from the NIC card to the firewall for processing. Also, we talked about fast path. Fast path is also called acceleration path, and so fast path is where the packet gets accelerated through the SecureXL level. And also, we talked about medium path. And for medium path, the packet has to be accepted by SecureXL level, but we need to do deeper inspection of the packet, so we have to forward the traffic to the passive streaming layer, where it assembles all the different packets that are out of sequence and assembles them in order for inspection. And I also mentioned that firewall path, slow path, is also known as forward to firewall, F2F. And the medium path, passive streaming layer, is also called F2P for forward to passive streaming layer. And in some places you also call it PXL for passive acceleration. And also we talked about some of the best practices. Now, depending on your traffic pattern, the traffic profile on your network, depending if the traffic is being accelerated through firewall path, you might need to have more cores being utilized for firewall instances, or the packet might need to go through the SecureXL acceleration, and so we talked about having more cores for the security network dispatching. And also, depending on the blades that you've enabled, like IPS blade, application control blade, you might need to have the packet go through medium path for deeper inspection after the packets have been assembled. And we discussed how medium path works in conjunction with the cores that are also processing the firewall traffic. Also, we talked about user space processes and how user space processes need to communicate to the kernel using the firewall instance 0. And firewall instance 0 will then communicate to the other firewall instances and aggregate the information and forward it back to the user space processes that need it. And we also talked about the policy and how the policy needs to be pushed to all kernel instances, and if any kernel instance fails, then it reverts back to the previous policy. And finally, we talked about some limitations. We talked about some VPN limitations and also some VoIP, voice over IP limitations. And we also talked about some parameters to make VPNs and voice over IP traffic being assigned to kernel instance 0, and other traffic will be assigned and distributed amongst all the rest of the cores. And that's about it. Those are the highlights of what we discussed in this chapter. We'll see you next time. Bye for now.
Checkpoint. We secure the future.